Okay, now it gives you 10 potential binding mode ranked by docking score. So check doc.txt and out.pdbqt. So this is a pdbqt file. It's a pdb file that you can visualize it. This is the output file. You can have a look at the output file first to check. So the output file will look the same as what you see on the command prompt window. Okay. In the out.pdbqt file, you cannot visualize directly. You have to do some little modification in this file. Okay, I'm going to open files. This is the out.pdbqt file. It looks like PDB format. It has a atomic coordinate for X, Y, Z, and this line associated with the atom name, atom type, and atom ID. So it looks similar, but it has a lot of truncation here. Okay, one of the easiest thing to analyze this, you run VNASPIT to convert this output file out of PDBQT into a more readable PDBQT file. Type VNASPIT, and followed by out PDBQT. Oh, need to pay input option. VNASPIT minus input, and then argument is out of PDBQT. Okay, once you run VNASPIT.pdbqt, you generate each binding post predicted from the Autodoc VNA. Let me next to see to make sure that this is readable. Okay, I can use the Autodoc tool to analyze the result. I prefer to use BMD. So I'm going to do some modification of this output. Okay, I need to use Linux. Need to program a little bit. Let okay. I may use this one. Okay. That's okay. Right. Then PDBQT. So what I need is to grab my containing atom. If I type PDBQT, that's result. And So this one M A E O T N B B B for the B already. And E M. Yes. Good. Good. Now dot say not PDB FQT. Okay, let's I like to check. This is the output. I convert into a different. So this model one is correspond to the binding pose of the first length. Model two is the second length. That means I can transfer this into okay. This is the output from docking, and it can be visualized using BMD. Okay, let's see. So this is the reference. Check. This is representation as let's remove everything here. If I choose protein, the PDB, okay, this is the protein structure. And if I choose ligand, this is a ligand, so the new molecule. And I choose ligand. Okay, this okay, I'm showing you right now is the protein. So it's as a cartoon, and the position of the ligand. This is I use it as a reference. Let's see it. Okay, next I load the output. Okay, modify. Good. I change the representation to localize and perhaps a change color. So yellow. Okay. Now you see the OpenGL display on VMD, and this is VMD main. And in this object tree, you see this is the docking pose, binding pose of the ligand, and we have a 10 frame. That means we have 10 binding pose for the ligand here. So this one is show you the last frame. If you want to check the other frame, you just load this one, go back and see, compare. We don't need to see the protein. You can hide the protein at the moment. See how close they are. This one, I think this is length number 2. This prediction is quite okay. What about number one? Number one is bad. Let's see. This is number one. No, this is number one. This is number two. This is number three. Okay, number three. Number three has give a nice prediction. So you can see from this prediction, the number three, which is the length three, does not give you the best score. See, the best score is length number one gives the dot score about minus 6.4. This is in terms of affinity energy. But length is give a better binding force. So what I would like to emphasize here is that when you do molecular docking, the best binding energy doesn't mean best binding result. So when you do molecular docking, you have to be careful about interpretation of the docking results. You shouldn't use only one software to do molecular docking. It's better to use a different docking algorithm to see how consistency of the docking result is.